Welcome back, CSCI 2021ers. This is a lecture to make up a little bit of ground and serve as a reference on the concept of memory mapped files, along with a few other tidbits associated with the virtual memory. We will begin this with an exercise we may have left off with at some point in lecture. It is to quickly write out a small program that would read in the characters from a file that's stored permanently and print them on the screen. The point of this exercise is to understand one key feature of that program. So if you have not already written such a program yourself, then have a look at one of the solutions that's provided in the code pack associated with this. That is in, for me, 2021 lectures. And then I have our virtual memory code in here. The name of this file is printfile.c. It has a short, simple structure, and we'll walk through it just quickly to point out one of the key features. You'll recall down here that the C features that allow one to open up a file are to use fopen, and then to later on use fscanf to, after you've opened up the file, get some data out of it. In this case, I'm reading characters individually out of that file, and this avoids any problems with reading in strings and missing white space and new lines and so forth from it. One of the key things to notice about this, though, is that I'm always responsible for providing a variable, in this case, in a car called incar, to place any data that's read from the file into. This usually means the following, that I have some storage space reserved in my program area, and these fscanf calls devolve to an operating system request to take some data that it's got stored in a file someplace and plop it down in that variable. This is mildly wasteful because in most cases the operating system has already taken parts of the file and placed it in memory someplace. This request in fscanf is just to copy memory in the operating system buffers the file into my program buffer. At any rate, this little nuisance is something that we're going to overcome, but the rest of the structure of the file is simply after reading to check if I've reached the end of the file or not. If so, break out, and if I actually successfully read a character, then to print it out on the screen. We can see how this thing works by jumping over to a terminal. I'll GCC my printfile.c and run it on this Gettysburg.txt file, which is the Gettysburg Address, one of Lincoln's most famous speeches. So looking at the contents of the file, it comes out character by character. This is very similar in ways to the cat utility that's common on Unix systems, which is to take contents of files and spit them out to standard output. So you'd see catting the contents of this would produce the same output on the screen. Now, we're interested in this to contrast it with an alternative. The alternative is also a program that's in your program pack. It is this mmap print file. I'll pop that thing open. It has a slightly more complex structure, but let's walk through it and observe a couple interesting things. First, you should know that mmap is not a standard C library function anymore. Unlike fscanf and fprintf and so forth, these aren't part of the standard C library, and the mmap and stat function calls are actually Unix system calls and will be guaranteed only to be present on those systems, although I hear that on Windows systems, for instance, these are also prevalent and can be used in a lot of cases. Suffice to say that once you start getting outside of the C standard library, you may reduce the portability of your C programs, but in this case, I think the utility of understanding how to use mmap is far outweighs any sort of concerns about portability. So you'll notice up here then, rather than using fopen in order to get some open file handle associated with the file, I've dropped down to a lower level call, a low level open call. And if you think all the way back to assignment 1, you'll have some recognition of this thing. It has similar calling semantics to fopen, in that the first argument is a string name of the file provided on the command line, and there's a flag here that strongly indicates that I'm reading only from this file, the open for read only flag here. This differs from fopen a little bit in that it's a low-level Unix system call and doesn't provide as much sort of surrounding infrastructure as the C standard library. The differences between those two are covered somewhat more in an operating systems class, such as our CSCI 4061. But suffice to say, this is a first step to setting up the mmap call. The next couple steps should also be familiar if you think all the way back to our first assignment. We'll use another system call called fstat, which will obtain some information about the file that I just opened. In this case, I have to provide some storage to place that information in, a stat buff, as it were. And we're most interested in this case in the size of the file in bytes. That, if you populate the stat buff with the fstat call, is in this little st size. And that gives me the number of bytes that's in the file, which will be used in just a second in the mmap call. Finally then, the real meat of this thing is the call to mmap that starts here at line 24. You can see that the results of this thing are going to return some kind of a pointer. And if you look at the manual for mmap, you'll find it actually returns a void pointer. I know that I want to treat the contents of this file as characters, and to that end I'm just going to cast, or in the case of mmap returning a void pointer, as it does, I don't need to cast, but treat that return as a pointer not to arbitrary stuff but to characters. And that will follow the method we just outlined in the previous file that allows me to work through that file on a character by character basis. The arguments that are mentioned here, the first null means assign a memory address to this memory mapping wherever the operating system finds convenient. The size here is what I obtained a moment ago from the stat call. There's some flags here that indicate how I intend to use the memory mapped region mentioned in the file descriptor, and this 0 here is an offset. Most of these things can be copy-pasted in a lot of cases, unless you wanted to, for instance, write to the file as well, in which case you need to add some flags over here. Now, the arguments aside, the main intent of memory map is to make a request, in this case, for the operating system to provide direct access to the bytes of this file it's already loaded up. In this case, by specifying this size argument here as the entire size of the file, this gives me a pointer essentially to a big array of bytes that are present in the file, and I have direct access to them. There's no need to copy anything from an operating system array into an array in this program. The pointer that's returned assigned to this file cars gives me direct access there. So subsequently, it's a very simple structure in order to work with this thing. I'll just have a standard little for loop. I know how many bytes are in the file, and on the assumption that's usually safe, that characters are single byte big, I can treat this thing as one big array of characters that are coming from the file, directly printing them. You notice here then there's an absence of any fread or fscanf or any other sort of ask to take stuff out of an operating system buffer file and plop it down in a variable here. Instead, I already have access to that operating system buffer through this file cars pointer. And here, as we've done many times before, treating that pointer as an array of characters. So at the end of this, I will print out. I have to do a little bit of cleanup to unmap that memory region and close down the file descriptor. But the net effect is identical to what I had a moment ago. Let me flip over to the shell again. I'll GCC this mmap print file and run that a.out, for instance, on the Gettysburg Address again, and see its contents printed out once again. So on that note, this mmap business is interesting in that it provides a new mechanism for input and output that we didn't have previously with fscanf and its ilk. That instead of asking for copies of things, we'll have to store in our program, at least temporarily, I am able to get direct access to file bytes. Now, there are a few other things that this provides, but right off the bat, you can see this is a very nice and convenient way to read files. That instead of fscanfing and potentially if I pass over something and want to back up on it, making calls like rewind and so forth, I don't have to worry about any implicit positions or movement of a file pointer within this context. Instead, I can treat the file directly as an array of bytes, and if I want to move forwards, as I did in this for loop, I just increment some variable, but I can also, for instance, print out things in reverse order just by starting I, for instance, at size -1, going for I greater than or equal to 0, and decrementing along those lines. This will start at the last byte of the file and print the entire thing out in reverse, something that's a bit tedious to do with an fscanf or other kind of implementation. Very trivial here, and if I GCC this thing and print it out, you'll see down here 7 years ago. Very easy in order to sort of print in reverse in this case. So that end, let me fix this thing up because I am always messing up programs like this and forgetting to change the back. The next thing that we'd want to potentially address with this differences between these two, and again, I'll sort of hint that the most important thing is the direct access that mmap guarantees, is that you don't just have read access with mmap. The reading that we can do is certainly convenient, but it also allows for writing, which is potentially useful in some contexts. You can set up the file characters that we had before, not just for reading, but for writing by passing an additional flag here, this protection write flag. Now you notice the little binary OR here, that this is a bitwise OR between some bit string that indicates read protection and write protection. So those OR together gives me both read and write access to the file bytes in there. And the interesting thing is then this array that is treated as arrays or characters that are in the file, if you make any changes to that array, you'll see changes to the actual file. An example of this shows up in this little mmap tr program. There's a classic Unix utility called tr, short for transliterate. Its function is to alter single characters and transform them into a second character. The meaning of that will become obvious in just a second. Before we get into the code, let's see the net effect of this thing. I will GCC this mmap tr.c file. If I run it without anything, you'll see a little usage. The usage for it is to run the program on a file, provide an input character and an output character. To that end, let me say a.out. We'll run this again on gettysburg.txt. And here for the input character, I'll choose the letter F and the output letter P. And you'll note a little bit of output here indicating what's been happening. Transformed all F's to P's. I'll do that likewise a second time for the lowercase version of these. As the result is just a little bit humorous, I'll cat out what gettysburg.txt looks like now, and you'll see that is poor score, and 7 years ago our fathers brought forth on this continent a new nation, blah, 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 blah. All the F's, both capital and small, because they did the transformation twice, have been transformed into P's. Now this is standard activity to do with utilities in C, such as fscanf. You could do this very easily using fscanf and reading character by character. It's a little tedious to do both the reading and writing. As you read things, you move forwards in the file. There's an implicit pointer in those file handles, and you have to back up a character to change what's there. On the other hand, with this mmap tr business, it's here. It is very straightforward to do. You can ignore a lot of the setup up here, which is just to obtain the file and the input and the output character. You'll notice down here that I have to open the file descriptor in both read-write mode, and that the M mapping down here looks almost identical, save for the fact that I am using this protection for read and write rather than just the read protection. But the central logic of the loop is super simple. You're scanning again through this array of file characters, And it's the case that if any character I see is in this scan, going by ones, is equal to the input character, I'm just going to make a change to it, to change the array of characters at that position to whatever the output character is. This write to that array of bytes is going to be backed up by the operating system to actually make changes to the disk file associated with that. And this is why, after running the program on gettysburg.txt, you see changes made to it. That it is memory mapped, and giving the program direct access to that will make changes to any bytes that are in the file that you'll see persistently. So to that end, mmapping is a really cool tool, super useful and extremely efficient in reducing overhead of moving around in files that can be sometimes inefficient with the standard C library I/O functions. It also reduces the memory overhead of many programs that deal with I/O stuff, because you no longer need to make copies of stuff from an existing operating system buffer for the file into program memory. No need to malloc anything or allocate a buffer on the stack. You instead get direct access to the bytes of those characters just by asking for a memory map here. It turns out that mmap is a very general utility and does not necessarily need to be applied just to characters. That it's an arbitrary way to say, take the bytes of this file and map them into my program in some way. A good example of this is in the mmap increment.c file, which we'll have a look at in just a second. Central to this is the fact that I can store some data in binary on disk. And it's the case, for instance, in the code pack, that you'll have a binary nums.dat data file. If you have a look at this thing in the terminal, let me cat out binary inst.dat, you'll see a bunch of gibberish in that all that's in here are binary integers. I don't remember exactly which values they are, but it's probably something like 1, 2, 3, 4, 5. And this is not easy to sort of handle in the text-based terminal. So this odd characters that are shown here are, again, the terminal's attempt to try and make some sense of these binary integers as character data, but it's failing fairly miserably for good cause. They aren't in the ASCII table in the way it's trying to interpret them. That is something that we could deal with, for instance, using the C standard fread function, which would grab out of a file the raw bytes and store them in an array, for instance, of integers. But it's also easily handled by mmap with a paradigm where I ask for a memory map of that stuff, but don't treat the bytes that I'm given as a pointer to characters, but rather a pointer to integers. This will then treat the file ints, as they're called here, as an array of integers, and based on C's idea of how big those integers are, it will automatically do accounting for sizes, like 4 bytes per int. So that later on, when I would access the integers in here, every access is multiplied by a size of 4, so I'm going to the correct positions in there. Let's have a look quickly at that mmap increment file to see that it's not particularly interesting except for the mmap setup over here. You can see that the same setup that we just saw a moment ago is to open up a file descriptor, again in read-write mode, as I intend to modify some of the bytes that are in that file, ask for its size, memory map the entire file, and then iterate through it as though this was just a standard C array of integers, printing them out and then incrementing them. At the end of this, the unmap and the closing the file descriptor guarantees that any changes that were made to that array are permanently stored in the file as well. We can look at the shell version of this, GCC, that's mmap increment. And run this thing on those binary ints.dat. You can see right now it has a value of 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. All of those were just incremented, though, according to this transformation complete business. That is over here the last part of this, so which is to iterate once through to print out those numbers and then iterate a second time through to add something onto them. That change in file bytes will be reflected as a permanent change to the file. So if I run this thing again, each integer has been incremented by 1. 5 becomes 6, 6 becomes 7, 7 becomes 8, and so forth. And if I just keep running this thing, I keep making changes to these integers, incrementing along the way. So it is the case then that mmap is often used not just for text files, but for binary files. This one is very simple. It contains just a bunch of integers in it, but in binary format. And it's the case that in one of your labs, you will study an application of this to a somewhat more complex data file that has a bunch of structs written to it in binary. Mmap is extremely useful for this kind of endeavor because you can easily look at that file as a bunch of bytes and then say at this location is a struct of this kind with a little bit of casting and a little bit of pointer arithmetic. You can easily then access data that's in that file and even make changes to it as may be done in one of your assignments. So there are a few things to point out in terms of disadvantages of mmap, but to quickly review, it avoids the cycle that you would be in with your standard I/O functions. That if you are attempting to use fread or fscanf, you will always need to have some sort of buffer in which you read stuff into for your program to potentially analyze or make changes to, and then if you're making changes to the file, you'd have to write it back to operating system memory in some way. There's a lot of coordination associated with this, a lot of intermediate space that's avoided through mmap, and so generally it's advantageous to make use of mmap in a lot of I/O settings. It turns out that many Linux mechanisms, including its standard facility to create memory that's shared between one or more programs, makes use of mmap as the underlying technology. So it's worth knowing about in that context too. We'll look at that in a short time with respect to how libraries are made available in an efficient manner to be shared amongst many different programs. The minor drawbacks associated with mmap are that it always maps whole pages of memory. This is because the virtual memory system, if you're making requests for your program to have its virtual addresses accessed some operating system buffer someplace, they're always done in these chunks, these page chunks of 4096 bytes. That's 4K. For lots of small files that you might deal with, for instance, here's a file that only has 100 or so bytes in it that you want to make changes to. It will be the case that a whole 4K chunk is essentially mapped in that case, and that makes for a fair amount of wasted space. It's also the case that mmap must be allocated with a fixed size, and if you are writing to a file to grow it, there isn't an elegant facility for mmap to easily grow with those writes. Fwrite, on the other hand, automatically extends files, and there's no need then to sort of make any other special calls to increase the size allocated. So if you're growing a file considerably, then mmap might not be the best choice, although there are some workarounds for that. Finally, like most things in C, there's no bounds checking associated with mmap. If you walk off the end of an array that's associated with the file, you may get into parts that are somewhat uninitialized, or you may go completely into a different page of memory, which will trigger a segmentation fault in your program. But if you've been programming in C for some time, you're probably used to those things already and expect there to be few safety precautions associated with this new mmap facility. All in all, mmap is a super cool tool and is extremely useful. It is well worth having in your toolkit as it addresses a number of interesting problems. The last little bit of stuff that we'll discuss here is to mention a few things about the virtual memory system at large. In addition to its ability to provide mappings of operating system buffers directly to programs, such as we saw with this mmap files, it's also possible for the virtual memory system to have pages of memory shared between multiple processes. It's the case that the operating system maintains one page table per process, and you'll recall that the page table is an internal data structure the operating system uses to figure out in one process's virtual address space which pages match to which physical pages. The isolated picture that processes have then is that according to their page table, for instance, process A, it has an address space that goes 00, 01, 02, and so forth, with these being page numbers. And the page table, which is really the operating system's responsibility to maintain, it has some physical pages number for that. But largely this allows the program to view its own world as having, I have some data stored at page 0, that's hell, and then at page 1, woo, and so forth. At 03 and 04, I have no data, and down here at 05, I have the little winky smiley face. Similarly, process B views its virtual address space as linear, and if you walk through and printed all these characters, it might go out of bounds at page 4 because that's not mapped, but would see similar sorts of stuff in terms of its layout there. But if you look carefully at the page tables for these two, you'll find that they are not that sequentially laid out. For instance, the page 00 of process B is mapped over here to page 3, so we haven't even started, and its next virtual page, 01, is mapped to 5, so there's actually a jump that's required to go over it. It's this fun business in the middle that's later on in the virtual address space that's actually in between those two. And if you look very carefully, you'll find that there is a little bit of shared data between these two. That their last virtual page, 5, is at physical page 7, and that's where both of these are sharing a smiley face. Now this interesting feature, as it were, would mean that if process A wrote a frowny face here, process B would see that as it would translate and look up what's at its virtual address 5. It would go to page 7 down here, and if process A had written a frowny face there, it would now see in process B a frowny face. So generally, most programs, and most processes that are loaded in, they don't by default share any memory with each other. There are system calls that you can make to arrange for this if you want two programs to cooperate and modify the same sets of data. But there is one exceptional case in which programs can freely share pieces of data without fear of stepping on each other's feet. And the important thing to realize about this is that that case must involve read-only memory. The most common use of read-only memory that process A and process B could share would be system libraries that do things like printf and scanf, or mmapping, or other system calls, C standard library calls like malloc, that are code to executes, but are not going to be changed by either of those processes. They call malloc and get memory in their own private heap, but they would never change the code associated with malloc. So it's the case then that the standard layout for a program in virtual memory has a stack, it has a data section, there's a heap down here that's managed by malloc, there's text area, but there's a special area that, at least in Linux systems, is present in the middle down here. And you'll see a couple replications here. In fact, I should probably increase the size of this for those of you who have low resolution or are hard of seeing here. You'll see up here in this shared memory area a mention of malloc.o with this lib.so extension. And down here a malloc.o with a lib.a. Historically, it was the case that when programs were compiled, they would receive copies of most system libraries, so they have their very own personal copy of malloc and printf and so forth. This was the traditional statically linked archive form of libraries. We will discuss this somewhat more when we discuss linking. A more modern implementation of this actually elides these, and when a program's compiled, it doesn't have any printf or malloc implementations in it. Instead, it relies on, at the point it's loaded, to be linked dynamically to some shared library. This usually means that a running system has one copy of malloc and one copy of printf that is shared amongst all of the processes that need to make use of it. And since pretty much every process uses the C library, this is a great savings because all of those processes would otherwise need their own copy of malloc and printf. If they're all sharing, then this is going to reduce the memory overhead on the system and create potentially more memory to do useful stuff like compute sums and matrices. To that end, though, this requires a bit of sophistication because it relies on this virtual memory system to say when the program is loaded, map part of its address space to where the libc is located. That gives the program access to things like malloc and printf. And otherwise, it will also need to have some of the addresses within it that access functions like malloc and printf adjusted to wherever those virtual addresses are mapped. But this means then that multiple programs can potentially share this system-wide library. And that'll be our next topic of discussion. The largely sort of block picture that you'd see associated with it is that the actual physical memory is one spot for printf and malloc and free and fscanf and so forth. But processes all think they own this themselves by virtue of this virtual memory mapping of some area where they want shared libraries placed being mapped to physical pages where those libraries actually exist. Finally, then, it is worthwhile to know about some utilities that show you some information about the memory map associated with programs. There's a nice utility on the Unix systems that we tend to run called pmap. It's a little utility program that, given the process ID of a running program, will give you what its virtual address spaces, what they're actually mapped on. So for instance, in a lab, you'll have a look at a little memory parts program. You compile this thing and you run it, and it will print out some addresses for things like an array that's in global memory, an array that's local to the main function, an array that's been malloced on the heap, and a memory mapped file. It'll then print out its own process ID. This is the number that the operating system uses to keep track of it as a running process, and then pause until you press a key. This gives you a chance in a different terminal to run this pmap utility. It requires that you provide the operating system PID, in this case 7986, and what will be printed for that program are all of the virtual address spaces that are currently mapped and tracked by the operating system. This is interesting because the addresses that are printed here are actually pulled right out of the page table, that walking through that interesting tree-like data structure and saying, what do I have in terms of virtual memory addresses that are mapped? These are all of them, along with the sizes that are associated with them. And the minimum size that you see along here is 4K because all page tables do is map individual pages. The minimum size then is based on page sizes. That's 4K. And you always see increments of 4 here, 8 here, or 16. In some cases, there'll be 12 down here. There are a few other interesting things to observe about this. For instance, we just got done talking about shared libraries, and you'll notice one right here. A large amount of space that is taken up by this program is its mapping to the C standard library. And those spaces aren't actually solely occupied by this program. Instead, this C library is stored at some place in system memory and is then mapped into the virtual address space by virtue of that page table here. What you aren't seeing, in the left-hand column here, you'll see the virtual addresses for those things, but you aren't seeing the physical addresses. I've tried a few times to figure out ways that you could see both the virtual address and the physical DRAM address for these things, but even on Linux systems where things are open, this is a little bit tricky to get at, and it may actually be a security risk to reveal it, so it may not be the case that anyone can write such a program. But what you can see about those memory areas is permissions associated with them. That, for instance, this area up here that's around 5579, this has read and execute permission. This is almost a sure sign that this part of the program, memory parts, this is probably the text area associated with it, where the executable instructions, those binary opcodes for assembly instructions, they are present and are being fed to the CPU. It's also the case that libc has some executable portion, and if you dug through there, that's probably where you'd find the definition for things like printf and scanf and malloc and so forth. It's also the case that there is some read-write and some read-only memory associated with the program. Very likely this RW is global data. And then some other parts over here are marked very clearly as, oh, this is the heap, something that wasn't in the stored memory program, but is needed at runtime. So there's some space allocated that malloc manages. It is read and write, but not execute, because data is stored in the heap that would be unsafe to execute there. Finally, down here you can see another runtime area, the stack. There's no storage of the stack in the executable file from memory parts because it's only needed at runtime. When the program is loaded up, another area is mapped and treated as a stack. If you look carefully at the addresses here, you'll see a local array here, and it's stored at an address that's like 7FF96 and so forth. And the stack right here also starts with 7FF96, indicating that, yeah, this local array very much is in the stack. It's close to the top of the stack in that respect. Versus this malloc array, which is at 0x5579, this is in the heap, which is mapped also to 0x5579, etc. There are a few other things. For instance, the global array up here, it is present in 0x5579A. That's probably down here in the read-write part. That's probably the data or initialized section of memory. So a lot of what's presented here in pmap in terms of the addresses of stuff, and when you cross-reference it to the actual virtual addresses the program reports for its stuff, they match up and confirm what we've learned about a separation of stack and heap and global data areas. We could also do things like print out the address of the main function, which would probably be in this memory parts text section that's executable. So have a good time in lab examining these things somewhat further, examining pmap as utility to give you information about the virtual memory pages that are mapped for a running process, and also looking at mmap as a way to quickly and easily parse some binary files.